In this video, we're going to look at 8 different examples which cover graphing secant, cosecant, tangent, and cotangent. And to save some time, I'm going to assume that you have some basic ability to graph sine and cosine functions, because that's the trick to graphing cosecant and secant functions. I'm also going to jump around a bit in the notes, so just be careful that you're looking at the same example as me. So we'll start with secant, and the trick to graphing secant is to know that it's the reciprocal of cosine. So to start, I'm just going to graph the parent cosine function. And then once you have cosine graphed, just think of what some of the reciprocal values would be on the graph. So like the first one here is at 1, and the reciprocal of 1, well, 1 is just a whole number, but if you put it over 1 to make it a fraction, flipping it over doesn't do anything. The reciprocal of 1 is itself. But once we get to this point here at 0, if you think of 0 being over 1 and then flip it around, you would get 1 over 0, and you can't divide by 0. So it's actually undefined here. So the secant graph is actually undefined at this point pi over 2. So I'm going to put a vertical asymptote there. There's no point on the graph that exists at pi over 2. And that's going to be the same thing for every point where cosine crosses over 0. So now we have all of these repeating vertical asymptotes, and we have all of these maximum points at 1, which, again, the reciprocal of 1 is still just 1, and the reciprocal of negative 1 is negative 1. So we have all these points in the middle of the vertical asymptotes. Now the thing to remember is that numbers that are close to 1, but right underneath it, the reciprocal of those values are going to be just a little bit bigger than 1. But if you think of a number here, that would be like 0.1. If I took 0.1, turned it into a fraction like this, and then reciprocated it, so just flip it around, you get 1 over 0.1. Well, 0.1 is 1/10, and dividing by a fraction is like multiplying by the reciprocal. So this would be like 1 times 10 over 1, which is 10. So all of that thinking here, all I was trying to figure out is what is the reciprocal value of this point at 0.1, and it turns out to be 10. So numbers that are close to 0 end up getting pretty big. So the reciprocal value of this point would be pretty tall. So this graph is just going to grow very fast towards this vertical asymptote. And the same thing is going to happen on the left. You can see there's some symmetry here. On the other side of this vertical asymptote, we have this minimum point, but this is going to grow down towards this vertical asymptote and down towards this vertical asymptote. So it's basically like we create these little parabolas. They're not actually parabolas because those don't have vertical asymptotes, but they kind of look like the same U-shape. So technically the secant graph is just what's in purple here, but when you graph these, it's okay to leave the original cosine graph in there as well. So now let's look at number 1, which is just a secant graph with a transformation. It's going to move left pi. But we're going to start by graphing y equals the cosine of x plus pi, so basically the equivalent cosine function. So I'll put my starting point for cosine, which is at its maximum. I'll put that at negative pi, and then it'll repeat 2 pi units to the right, which would be at positive pi, and then I'm just going to graph this cosine quickly. And then all of the 0 points will turn into vertical asymptotes. And then all these peak points will grow up towards the vertical asymptotes on each side, and all of the minimum points will grow down towards the vertical asymptotes on each side. Now since the secant graph is just the reciprocal of cosine, it has the same value for the period, which would be 2 pi divided by b, and in this case the b value is just 1 there, so it's just going to be 2 pi. And you can see on the graph, if you started at 0, if you just cut the graph off here, it starts by the right side of this bottom U shape, and then it has this top U shape, and then at 2 pi, if we just cut it off there, it has the bottom left side of the U shape. So this has like all of the pieces of the graph just once, and then after that it starts to repeat the pattern. The middle line is just y equals 0, because there was no vertical shift, and actually I'll answer that right away. The horizontal shift was just left pi. And now the range is a little bit tricky to answer with these, because I just want to answer what the range of the secant graph is, and that's just all of the red parts of the graph. So you can see that the top half of the graph, it goes up towards positive infinity, but it stops here at 1, and there aren't any values less than 1 until we get down here to this point at negative 1. And then it has all these negative values that are less than negative 1, but there's this weird gap in the middle. So to use interval notation to write out the range, I need to actually write it in 2 pieces. The bottom piece would be negative infinity to negative 1, and I'm going to put parentheses around the negative infinity because you can never actually reach that value, but at negative 1 it does include that on the graph, so I'll put a bracket around that. And then the top piece of the graph starts at positive 1 and goes off towards positive infinity. And again, we can't actually get to positive infinity, so I'll put parentheses around that. And that's how we write the range. These equations did not have any negative in front of them, so there's no vertical reflection. The next example has us graphing cosecant, basing it off of the sine graph. So we'll do just like we did in the first example. Once you have your sine function graphed, you just look for all of those 0 points, or where it crosses over the equilibrium line, and we turn those all into vertical asymptotes. And the cosecant graph has basically the same shape as secant. It starts at the maximum point here from sine, and then grows up towards the top of the vertical asymptotes, and then the minimum points grow towards the bottom of the vertical asymptotes. And that's your parent function for the cosecant graph. The main difference between cosecant and secant is cosecant starts with a vertical asymptote here at the y-axis, whereas the secant graph started with a point at positive 1 on the y-axis. So now let's jump to example number 2, which is y equals the cosecant of x minus pi over 2 plus 1. And we'll start by graphing the sine of x minus pi over 2 plus 1. So this graph has a middle line of positive 1, so I'm going to put a dashed line there. And this is moving right pi over 2, and sine starts with its equilibrium point. So going right pi over 2, I'll put a point right here on that middle line of the graph, and then graph the rest of the sine function. Now that I have the sine function graphed, we'll put all the vertical asymptotes in where the sine function crosses its equilibrium point, because that's where its reciprocal value would be undefined. And then we just have to graph all of those little parabola pieces. And just like the period of the sine graph is 2 pi, this one is also at 2 pi, and the b value is just 1, so that doesn't affect anything. The middle line though was y equals positive 1, and that was due to the vertical shift. The horizontal shift was right pi over 2, and the vertical shift was up 1. Again, the range is a little bit tricky to write, so in order to write the bottom part of the range of the graph, this starts at 0, and it does include that value, but it goes down towards negative infinity, which we can't ever reach, so we'll go parentheses, negative infinity, to 0, and then brackets around the 0. Now the top half starts at this y value of positive 2, and then goes up towards positive infinity, so bracket around 2, and positive infinity, and then parentheses. And this graph did not have any vertical reflection because there's no negative sign in front of these functions. Now graphing tangent and cotangent are very different, so let's take a minute and think back to like the unit circle, and what we know about tangent values on the unit circle. So let's start with the angle 0, and that's the point 1 comma 0. We can't actually make a triangle out of that, so we just use the point 1 comma 0. You got to remember that tangent is sine over cosine, and also that the cosine value is like the x value, and the sine value is just the y value on the unit circle. So our first tangent point for the angle 0 would be y over x. That would be 0 over 1, and that's also just 0. So the tangent of 0 is just 0. Now as the angle starts increasing, remember that tangent is y over x, and that's basically the slope of whatever the angle is. So you can see at first it's not a very steep slope, it's a pretty small number, but then as the angle starts increasing, the slope starts increasing pretty fast. As the angle starts to get close to this vertical line, the slope ends up being pretty steep, it's a pretty big number, and then once it is actually the vertical line, that's an undefined slope. So at tangent of 90 degrees, or in radians, that's pi over 2. Tangent of pi over 2 is undefined. That means there's going to be a vertical asymptote there. And as we go from 0 to pi over 2, the value is increasing. And when we graph these, remember the x value is always the angle, so we can think of negative x values on the actual tangent graph. We can think of those as negative angles, which just means that we're measuring in this downward direction. So again, the angles start out with a pretty small value. It's a negative slope, but they have a pretty small negative slope. And as they increase to negative pi over 2, the slope is increasing in a negative direction. It's getting really big in a negative way. So at tangent of negative pi over 2, the value is also undefined because that would just be a vertical line going straight down, and that would have an undefined slope. As we go from 0 to negative pi over 2, the value of the slope is decreasing. So let's use all of that to start graphing this tangent function. We said tangent of 0 is 0, so it starts at the origin, and then we said at pi over 2 there would be a vertical asymptote because that's where it was a vertical line, like the angle was a vertical line, and the value was undefined. As we went from 0 to pi over 2, the tangent value is increasing, so it's going to approach the vertical asymptote in this direction. As we went to negative pi over 2, there was also a vertical asymptote, but it was approaching it in the negative direction. The slopes were getting gradually increasingly negative. And if we think just quickly about the unit circle again, as the angle goes from pi over 2 closer to pi, well, now we start to have really big negative slopes. We're going in this negative direction. I know the angle is pointing up, but it has a negative slope, reading from left to right. And then as the angle goes closer to pi, the slope gets less and less steep. It's still negative, it's always negative, but it's less and less steep. Once we get to pi, it's at 0. So I'm going to put a point at 0, comma pi. And remember, we started with really big negative values. So I'll start with really big negative values down here, and we'll get gradually closer to 0. So the graph follows the vertical asymptote from the bottom up to pi. As we go in the positive direction around the unit circle, we go from pi closer to 3 pi over 2. The values start to have these positive slopes, and they get bigger and bigger and bigger until they get undefined again. So at 3 pi over 2, there's another vertical asymptote, and the graph approaches it in the positive direction. So now you can see this is the pattern that just keeps repeating. What's interesting about the tangent function is it's the first one we've seen that has a period of actually just pi. It goes from negative pi over 2 to positive pi over 2. So you can think of having half a pi in the positive direction and half a pi in the negative direction, and altogether that makes 1 full pi. So the period is just pi. All of the other ones have been 2 pi. But once you have one period of the function graphed, it's easy to just repeat that pattern. So I'll go out pi units again. That would bring me to negative 3 pi over 2, and I'll put another vertical asymptote there, and then just repeat the pattern. And that's the graph for the parent tangent function. So now we'll jump to example number 3, which is tangent of x minus pi over 2. There's no b value other than just 1, so the period is what it should normally be for the tangent function, which we just saw as pi. The middle line is y equals 0 because it wasn't shifted anywhere, so I'll actually write none for vertical shift. And the horizontal shift, since it's minus pi over 2, that'll bring it right pi over 2. And looking at the shape of the original tangent function, you can see even if we moved it left or right or up or down anywhere, it approaches these vertical asymptotes forever in the positive and negative direction. So for any tangent function, the range is just all real numbers. So I'll just answer that right away. And there's no vertical reflection here. So you can see the original tangent function has its middle point at the origin at 0, 0. This one was moved right pi over 2 though, so I'll put its middle point at pi over 2. And then I know that the period is pi, so I'm going to put a vertical asymptote at 0 and a vertical asymptote at pi, and that puts this middle point centered perfectly between those two vertical asymptotes, and then just make the graph approach it from the positive direction to the right and negative direction to the left. So this graph is always increasing. And once we have that one period of the graph graphed, we can just repeat that pattern. So I'll go another pi units to the left and put another vertical asymptote there, and we'll do that one more time at negative 2 pi. And then just making sure the tangent function goes through its middle point where it's supposed to and approaches the vertical asymptotes in the direction that it's supposed to. That's all you really have to do to graph these tangent functions. So this is the graph of tangent of x minus pi over 2. Now what's weird about this is that's actually exactly the graph of the cotangent function. So this has a vertical asymptote right on the y-axis, and that's the same as the cotangent function. We'll put a vertical asymptote right there on the y-axis. And that's because, again, if you think of the unit circle, the first point, the angle 0, is the point 1 comma 0, and tangent was the y divided by x value. So that was 0 divided by 1, but cotangent is the reciprocal, and that would be 1 divided by 0. So at the angle 0, the first cotangent point is actually undefined. But the cotangent graph has the same period as tangent, it's pi. So we'll put another vertical asymptote at pi and 2 pi, and then same thing going to the left. Now we'll reference the unit circle just one more time to think about what these cotangent values are doing. So the first cotangent value was undefined, but let's think about like pi over 4. That's right between 0 and pi over 2. So like somewhere between 0 and pi over 2. Let's see where the graph is going to be there. Well, this is the point square root of 2 over 2 comma square root of 2 over 2, because that comes from like our 45, 45, 90 triangle. And so the tangent value would be the y divided by the x, and they're the same value. So regardless of the way you divide them, they would just be equal to 1. So the tangent, like the slope here, is exactly equal to 1, and the cotangent, the reciprocal value, is still just equal to 1. So at pi over 4, this graph has an output or a y value of 1, positive 1. So the cotangent graph actually starts from the vertical asymptote and decreases until it gets to 0 at pi over 2, and then keeps decreasing. So when I said that the last graph was exactly the cotangent graph, I was a little bit off. This one actually decreases instead of the always increasing tangent function. Again, once you have one period of the graph graphed, you can just keep that pattern repeating. So it starts from the vertical asymptote decreasing through 0 right between the two vertical asymptotes, and that's basically the characteristics of the cotangent graph. So example number 4 is the cotangent of x plus pi. So adding pi on the inside of the function, that's actually going to move it left pi units. So the horizontal shift is just left pi. It hasn't been moved up or down anywhere, so the middle line is still just y equals 0. And the period is relating to the b value, which is 1. So just like before, the period is just going to be pi. So we're going to think of taking this first point on the cotangent graph, which isn't actually a point, it's just a vertical asymptote. We're going to start by taking that thing, and we're going to move it left pi units. But what's kind of funny is if you go left pi units, that's where the other vertical asymptote is. So it's like we're taking the original vertical asymptote here and moving it right onto where the other vertical asymptote would be anyways. So this graph is actually going to look exactly the same as the original cotangent graph. Really quickly, I'll just write that there's no vertical shift, and the range is all real numbers because, again, the graph goes up and down forever, no matter which way you move it around. So then just making sure that it crosses through the middle line at 0, right between the two vertical asymptotes, and is decreasing from left to right, you can just graph your cotangent function like that. And there's no negative in front of this function, so there's no vertical reflection. If there was, it would end up being an increasing graph, so it would actually look a lot like the tangent graph. So just to quickly summarize these couple graphs, graphing secant and cosecant just relies on graphing the reciprocal functions first. So you always graph sine or cosine accordingly, and then just the equilibrium points turn into vertical asymptotes. With tangent and cotangent, you just have to know if it starts with 0, so tangent always starts at its 0 point, and cotangent starts with its vertical asymptote. And then just knowing that tangent is an increasing graph and cotangent is decreasing. And those are the basics of what you need to know for graphing cosecant, secant, cotangent, and tangent.